Students, in last class we discussed about the rectifiers and classification of rectifiers. In that we discussed about the off-wave rectifier, its operation. Then after we discussed about the some of the parameters of off-wave rectifier. Today we will discuss about the voltage. How much DC voltage drop across the diode in the off-wave rectifier? Yes, we can say DC is nothing but average value. So we can define as it's the average value of instantaneous voltage drop across the diode. Yes. First, we should know the how much voltage drop, how much pulsating voltage drop across the diode. Then after, we can calculate the average value of that. It is nothing but DC voltage. Yes. First, we should know how much voltage drop across the diode. Then after, what are the voltage drop finding across the diode? For that, we need to calculate the average value. Yes. So first, we should know the how much voltage drop across the diode. So it can be calculated by considering the two cases. Why? Because here we are applying the one complete cycle is 0 to 25. In this 0 to 5 we are applying positive half cycle. In 5 to 25 we are applying negative half cycle. Yes. So in this first case we are considering 0 to 5. 0 less than alpha is less than 5. So in this case we are applying the positive half cycle. In this time period diode is in forward bias. So when the diode is in forward bias, the resistance offered by the diode is very small. We know this RF is very small. So the voltage drop across the diode can be calculated. Current passing through the diode is multiplied with the resistance offered by the diode. So the product is I into RF is almost equals to 0. So we can say voltage drop across the diode during the time period of 0 to 5 is 0. In next case, we are considering the 5 to 25. It is nothing but 5 is less than alpha is less than 25. So in this case, we are applying the negative half cycle. So in this time period, diode is in reverse bias. So when the diode is in reverse bias, it is open circuited. So whatever we applied input voltage, that same will be appear across the diode. So we can say voltage drop across the diode. B diode can be written as VI. It is input voltage. So we are considering VI equals to Vm sin alpha. So we can say voltage drop across the diode equals to Vm sin alpha during the time period of 5 to 25. So we can say voltage drop across the diode is 0 in the time period of 0 to 5 and Vm sin alpha in the time period of 5 to 25. So now we need to calculate the voltage drop. DC voltage drop across the diode, it is nothing but V diode DC is average value of V diode. Yes. So V diode DC equals to 1 by 25, 0 to 25 V diode D alpha. We know this formula. Now we are substituting the values. So 1 by 25, 0 to 5 V diode equals to 0, 0 into D alpha plus 1 by 25, 5 to 25 Vm sin alpha D alpha. So by integrating the sin alpha, we can get the minus cos alpha. Now the limits are 5 to 25. By substituting that values, we will get DC voltage drop across the diode. It is V diode DC equals to minus Vm by 5. Yes, where no load DC voltage. That means there is no current flowing through the load resistor. Otherwise, you can say when load resistor is infinite, it means open circuited. Clear? So it's the DC output voltage obtained when load current is 0. So it is VDC NL is nothing but VDC when IDC equals to 0. Otherwise RL equals to infinite. So you can say the circuit diagram by applying the KVL. So it is equals to minus 0 plus VDC diode plus VDC NL. From that we can say VDC NL equals to minus V diode of DC. Minus of minus it is plus, it is becomes Vm by 5. And second one, it is full load DC output voltage. That means now we are considering the DC output voltage when RL is present. Otherwise, you can say it's the DC output voltage when load current is non-zero. Yes, now it is VDC FL equals to VDC when IDC is non-zero. So it can be written as simply VDC equals to IDC into RL. Yes, VDC FL equals to IDC into RL when there is no voltage drop across the diode and secondary winding. But coming to practical, you can say when load current is flows in this circuit, there is a DC voltage drop across the diode as well as secondary winding because of their internal resistance. Because of their internal resistance. So here I mentioned it is a voltage drop, but you may consider it as a internal resistance. So we can say in this VDC FL is also equals to VDC NL. That means there is no load voltage drop across voltage drop at the output when there is no load. It is VDC NL minus internal voltage drop. Yes, internal voltage drop occur at diode as well as secondary winding. Why? The diode is offering the forward resistance, it is very small RF, and secondary winding offering the resistance, it is RSW. Yes, so we can say VDC FL equals to VM by 5 minus IDC into R. Clear? So here R is nothing but forward resistance of the diode and resistance offered by the secondary winding. Now we are substituting regulation factor. What do you mean by regulation factor? This regulation factor is nothing but is the change in DC output voltage due to the change in load current. Yes. So otherwise you can say change in the output voltage when load changes from the no load to full load. It is mathematically represented as regulation is nothing but VDC NL minus VDC FL by VDC FL. Yes. So now we are substituting here. We already know VDC FL, it is also nothing but VM by 5 minus IDC RL. So because of internal voltage drop in the circuit. Yes. So here I am writing VDC/FL equals to IDC into RL. So it is also same when there is no internal voltage drops. So from that we can say percentage of regulation equals to R by RL into 100. Here R is nothing but resistance offered by the diode, it is RF, plus resistance offered by the secondary winding. Clear? If diode and winding are ideal, then regulation factor becomes, what happens? 0. Why? Because the R becomes 0. Yes. If ideal diode, we are considering the ideal diode, that RF equals to 0 and ideal winding, then RSW equals 0. So which implies that DC output voltage does not vary with load current. Clear? So from that we can say when you are considering the ideal diode and ideal winding, there is no internal voltage drop. That means that capital R becomes 0. So from that we can say DC output voltage does not vary with the load current. Remember this one. It may helpful in further. Voltage. It is the maximum voltage which appears across the diode. Clear? When the diode is in reverse bias. First, peak inverse voltage is nothing but it is the maximum voltage which appears across the diode when it is in reverse bias, otherwise when the diode is in not conduction. Yes, otherwise you can say the maximum voltage drop appears across the diode in reverse bias, otherwise how much voltage it can allow in the reverse bias before breakdown. Clear? So what is the maximum voltage drop appears across the diode in the reverse bias? It is nothing but before breakdown voltage. Clear? It is the peak inverse voltage. This peak inverse voltage is nothing but V diode maximum. What are the voltage drop across the diode? It is a maximum voltage drop in reverse bias. We already know this V diode equals to Vm sin alpha. Yes, in reverse bias. It is sin alpha. The maximum becomes when alpha equals to 90. Now it becomes peak inverse voltage equals to Vm. When you are applying more than Vm voltage, the diode may damage. Clear? After peak inverse voltage, the diode must be enter into the breakdown region. That means the junction may damage. Next, form factor. It's the ratio of RMS value to the average value. It is nothing but IRMS by IDC or VRMS by VDC. Anyone. Yes. So it is ratio of IRMS by IDC. So we can say IRMS equals to IM by 2, IDC equals to IM by 5. From that we can say form factor F equals to 5 by 2. This value is 1.57 in the of a rectifier. So next, relationship between the ripple factor and form factor. We already know the ripple factor equals to RMS value of AC component in the output voltage. This is nothing but I dash RMS by IDC. So this I dash RMS is already known. I square RMS minus I square DC. So IDC in root we can say I square DC. So from that we can say I square RMS by I square RMS by I square DC minus 1. So it is nothing but ripple factor equals to under root of form factor square minus 1. It is nothing but R equals to F square minus 1. We know ideally ripple factor equals to 0. Yes, ideally ripple factor equals to 0. What could be the form factor? Yes, R equals to 0. That means F square minus 1 equals to 0. Now F equals to 1. Yes, so ideally ripple factor equals to 0. Form factor equals to what's the frequency of output signal? Clear? So here you can observe the output waveforms of a rectifier. So we can get the off cycle, off positive cycle in the output waveform. During the negative cycle, it is reverse bias. It will not appear in the output. So during the time period 0 to 2 5, we are getting only off cycle, positive cycle only. Yes. So it is input and output waveforms have equal time period. Yes, you can observe 0 to 2 5 and 0 to 2 5. It has the equal time period. Therefore, frequency of output is same as applied AC frequency. Yes, whatever we applied the AC signal frequency, that same frequency will appear at the output also. So we can say this frequency of output or output frequency also nothing but line frequency. It is almost equals to the F naught. It is fundamental frequency or input frequency. Yes. So this output wave is, we know it is a non-sinusoidal signal. When we are having the non-sinusoidal signals, these non-sinusoidal signals are always having the harmonic frequencies. Yes, multiple frequencies. These harmonics can be known from the trigonometric Fourier series. Yes, trigonometric Fourier series representation of output waveform. So it is represented as V0 by V0 equals to Vm by 5 plus Vm by 2 sin omega naught t minus 2 Vm by 5, and k is even sum of cos k omega naught t by k plus 1 k minus 1. So k is even. So when I'm considering the k equals to 2, now it becomes cos 2 omega naught t by 3. So here cos 2 omega naught. Next, when I'm considering the k equals to 4, then cos 4 omega naught. So in this output voltage, we can identify omega naught frequency term and 2 omega naught, 4 omega naught, 6 omega naught, 8 omega naught terms. Yes, this AC components having the fundamental frequency of fundamental frequency nothing but whatever we applied, it is omega naught. Along with we are having the even harmonics that are 2 omega naught, 4 omega naught, 6 omega naught, 8 omega naught. Yes. So in this we are saying it is a pulsating DC. It has DC component, it has Vm by 5, it is DC component. The remaining terms are indicating the AC component. In this AC we are having the fundamental frequency as well as even harmonics. Yes. So what are the even harmonics that are unwanted AC components? That unwanted AC components are eliminated by using the filters. Yes. So we'll discuss about the filters in next classes. Next, we'll discuss about the utilization factor. Yes, so it is nothing but it is always indicated the how much we are utilizing the transformer. Yes, it's the ratio of DC output power and AC rating of secondary winding. So how much power delivered by the secondary winding, from that how much we are getting DC output power. Yes, it's the ratio of DC output power delivered by the of a rectifier to the AC power delivered by the secondary winding of our transformer. Yes, so we know output delivered by the ultimate we need to get the DC power. Yes, so the power delivered by the of a rectifier is DC PDC, and secondary winding rating, power rating is nothing but AC rating is nothing but RMS voltage across the secondary winding and RMS current through the winding. Yes, so we can say transformer utilization factor is defined as PDC by AC rating of secondary winding. Yes, so we can write the AC rating of secondary winding is nothing but RMS value of voltage and RMS value of current in general. So we can say power rating of power delivered by the DC power delivered by the circuit is PDC. It is nothing but I square DC into RL. Otherwise, we can say VDC into IDC. Yes. So here I am writing it is I square DC into RL. We know I square DC equals to I square M by 5 square, and PAC or power delivered by the secondary winding is nothing but AC power. It is Vm by root 2 is RMS value and Im by 2. So in this we can say I square M by 2 root 2 into RF plus RL. Clear? So now we can write TUF equals to 2 root 2 by 5 into RL by RF plus RL. Yes. So it is equals to 0.286. Clear? When RF equals 0, if I am assuming my resistor, my diode is ideal, the drop across the diode is 0. So RF equals to 0. Power resistance offered by the diode is 0. Then transformer utilization factor is 0.286. It is the maximum. Yes, how much percentage we are utilizing? Just 28.6% only. Yes, so this is the transformer utilization factor. Next, what are the advantages and disadvantages? Yes, advantage and disadvantages of a rectifier. So in this circuit we are simply using only one diode. So here we are using only one diode. Yes, the diode circuit designing is also very easy. The circuit is to design very easily. Yes, the circuit can be designed very easily. Why? Because here we are having not that much complex. One diode and one step down transformer and load resistor. Here we are not using any semi-tapered transformer. And disadvantages of a rectifier. So in this output we are having more ripples. That means the ripple factor is always sitting the amount of AC components in the DC. Yes, so ripple factor is too high, it is 1.21. Yes, and efficiency of the rectifier is also 40.5%. It is very low. When you're considering 100%, 100 out of 100 we are getting only 40.5 only. It is very low. And transformer iteration factor, it is also very low value. It is 0.287 only. That means we are not using fully. Yes, transformer iteration is also very low value. These are the main disadvantages in the of a rectifier. Due to these reasons, we are moving into the full rectifier. Yes, we'll discuss in next class. Thank you.